Hello and welcome to Through the Telescope, the podcast that puts the lens on astronomy. I'm Rose Waugh and I'm an astrophysicist and science communicator.
And I'm Elliot Bruce, and I'm neither of those things, but I'll be trying to find out why we should even care about astronomy. We'll be exploring some of the big topics in the field in little manageable pieces and have some fun along the way.
So, whether you know your red giants from your red shifts, or you're not quite sure what the difference between astronomy and astrology actually is, join us as we launch ourselves into the cosmos and try not to burn up on re-entry. Through the Telescope is sponsored by PicAstro, the astronomy and astrophotography image sharing app, dedicated to your images of the cosmos no matter what stage you are on your journey around the universe. No ads, spam, or fake accounts.
So, Ro, last time we talked about the levels of the sun and kind of where it's come from and where it's going. But we actually ended up talking so much during the recording of the last episode that we have some extra stuff to talk about. So
The sun is very interesting. It's got a lot going on.
it does. So in this episode, we're going to be talking about solar activity in all its forms.
Well, not all its forms, but
Okay, fine.
yeah. We're talking about some aspects of solar activity.
So let's go. So you talked about nano flares.
Mm-hmm.
What are big old flares like? A lot of activity.
Similar, but big.
Makes
really.
sense.
Again, they're just intense bursts of energy and light that comes from the surface, and they appear to us as bright regions that, they're visible from anywhere from for a few minutes to hours.
Okay.
And you can see them in all wavelengths of light.
Oh, okay.
So they emit a lot of light. And generally we monitor them in X-rays and visible light, though we don't tend to look at them in other.
Is that just like there's
things.
less of a background or something? Or there's just more energy, makes everything
make a
easier?
lot, yeah. So that's pretty much what they are. They're just big. They're flares. I feel like that one's relatively self-explanatory. Once someone has defined it,
Yeah.
the name is quite descriptive.
So is a flare the same as a prominence?
No.
What's a prominence?
A prominence is a big clump of material from the star, so hydrogen,
Okay.
that has condensed. So it's got more dense. It's kind of turned like into a cloud. If you think of like the Earth's atmosphere,
Mm-hmm.
if you cool down a certain region of the atmosphere, you get a cloud.
Right.
The water in the atmosphere turns into a cloud. It's a similar kind of thing, but with hydrogen on the sun in its atmosphere.
Hydrogen
Atmosphere,
clouds.
inverted commas. And they form along magnetic field lines. So typically you see them as big loops.
Ooh.
So you might have seen pictures of them.
Yeah.
And they look like loops of generally like orangey red clouds.
So that's not a flare, that's a
that's a prominence.
Okay.
Yeah, they stick around for significantly longer than a flare, and they're made of, star material rather than being like emissions of light.
So do they let out less energy then? They're just sort of a feature.
Yeah, they tend to kind of float around. Don't do very much for a while. So there are two types of prominences: active prominences
and inactive prominences.
and quiescent prominences.
That's a way cooler name. I'm
Active
not lazy, I'm just quiescent.
Active prominences are those that are going to do something, and quiescent prominences are those that are pretty stable and aren't going to do something until they do, because they,
Right.
they get destabilized by
Right.
things. And doing something means either, kind of falling apart, collapsing back to the surface,
Okay. That doesn't sound like doing much.
draining back to the surface, or being erupted.
Okay.
So you might hear the term eruptive prominence sometimes, or erupted prominence. And that's when your prominence material is like flung into space.
Sounds like you need to go to a doctor at that point. Is that a coronal mass ejection? I've heard of that one.
I laugh because a large amount of my PhD, it feels, has been spent trying to understand the difference between an erupted prominence and a coronal mass ejection. You think you're asking a straightforward question,
Yes.
but you're not.
Why not?
I don't know. I don't know if anyone fully understands the difference.
Okay.
I don't know if it's a classification thing from, throughout history, things have been classified in a certain way, or if I'm just being an idiot and no one can ever answer this question for me. I don't think it's entirely that one, though. I suspect that erupted prominences are a subset of coronal mass ejections.
Okay, because I was going to guess the other way, because I guess it's because it's coronal mass, but I guess mass is the amount of, like the mass, like weight, as it were. Even though mass is not the same as weight, but you know what I mean? Like, is it coronal mass ejection as opposed to coronal mass, like coronal lots of ejection?
Always interpreted it, or matter, from the corona.
Matter, that's the best.
That is ejected.
Right, coronal matter ejection as opposed to coronal humongous ejection.
Yes.
Okay.
CMEs are not... CMEs, which is the shorthand for coronal mass ejection, can cover a wide range of masses and energies, really. I mean, everything's relative, again, so... But you can get big ones or small ones.
Okay. So then, is it that when you say that you think that erupted prominences are a subset of that, is that there are other things that could eject?
Potentially.
Like a flare? Does a flare eject? Is that just light? Does that also eject some stuff?
Some stuff can be ejected during a flare, but typically flares are a result of magnetic reconnective events.
Ooh.
That result in lots of the highly charged particles, like electrons, being channeled very, very, very quickly down the magnetic field line to the base of the field line, to the foot points that we were talking about at the surface. And then this producing a lot of different types of light and various types of X-rays.
Okay.
Some of which come from the motions of the electrons, and some come from other things, because, you're firing electrons very quickly to the surface of the sun.
Is it?
There are going to be collisions.
Is it one of my favourite words? Bremsstrahlung.
Yes, yeah, there's Bremsstrahlung
Or
radiation.
braking radiation.
Amongst other things. It's mostly really what a flare is about.
So we've had flares, we've had prominences, we've had CMEs. What else are we getting? Is there any other kind of like space, I don't know, style, like geography or weather or anything going on?
So you can get there's a whole bunch of random stuff, I suppose. So geography wise, I guess you're asking about things that would be on the surface of the star. So you could get things like granulation. So if you look at pictures of the sun on Google,
Other search engines are available.
or other search engines, I was just thinking that.
Don't use Bing though.
That's
not the one.
Well, you can, but you probably won't find what you're looking for.
Use Ask Jeeves.
Is that still going?
I don't know.
if you look at pictures of the sun on your, preferred search engine, you'll find that it's all speckled.
Okay.
Some bits of it are a kind of darker orange or whatever colour filter you're looking at, and other bits are more yellowy or lighter, whatever colour you're looking
Kind of like a margarita pizza with not a huge amount of cheese.
at. Maybe.
Okay. No basil either.
Are you hungry?
I'm getting hungry now to have a pizza.
Okay. So you get a kind of speckled look, and that's called granulation, and that's to do with the convection. So the hot bits bubble up to the surface,
Okay.
and then the cooler bits start to sink back kind of through the surface, if you like.
So is that a consequence of the convective zone being
Yeah.
above the radiative zone?
And so you get this kind of convection pattern, which is called granulation.
Okay. Oh, is it a bit like when you boil something on the hob and you get especially something
Yeah,
thick,
the bubbles come up.
the bubbles come up and then it's sort of, there's sort of
And then some bits sink
between
down.
the bubbles that are, nice. So you're watching the sun when you're doing your cooking there.
Yeah, same thing. Same bit of physics.
Nice.
You also can see sunspots.
Okay.
So sunspots are dark spots on the surface of the sun.
It does what it says on the tin.
Yeah, also quite self-explanatory. And they're regions of very intense magnetic field.
Okay.
And that's what causes these dark spots on the surface.
Right.
Because wherever you get lots of magnetic field, very intense magnetic field, you can think of that as having, many, many magnetic field lines going to that point. And that section of the surface gets kind of essentially cut off from other bits.
Right.
Because all of your sun is made of plasma, so it's all every particle in the sun is charged.
Yeah.
And charged particles are confined by field lines. So they can travel along field lines, but they can't pass from one field line to another one. They can't go sideways.
Yeah.
They can only go along field lines.
And they do a little kind of, well, it's not a spiral, is it? It's a helix.
Yeah,
right?
around it. But that doesn't really matter too much.
Yeah. But the point is they're stuck on one field line, they can't move.
Yeah, so if you have regions of very intense magnetic field, it kind of singles out, it cuts off that bit of the surface from everywhere else.
Right, so then...
And they tend, the temperature tends to drop, and that leads to dark spots.
Because it can't get any extra energy from neighbouring bits because it can't essentially talk to neighbouring bits. That's interesting. So the magnetic field then dictates, at least in part, the temperature of different bits of the sun, or different bits of the surface of the sun.
Yeah.
That's interesting.
Well, the magnetic field dictates pretty much everything about the sun, really. That's why it's important. It dictates how any charged particle in the sun, which is pretty much every bit of the sun, can move about the sun. So, yeah.
Quite important. I guess I would have just thought, completely not knowing anything, some bits are cold because they're cold. But that's neat. Do you say magnetic trapping? Or
You could call it that.
I'm going to call it that.
Call it that, but you could do.
Magnetic thermal traps. That's my name for it. I'll come up for it. I'm going to write in my paper about
that and the coronal heating problem. All right.
What was my answer to the coronal heating problem?
I don't know. You'll have to listen back
I'll
and write it down.
I'll write in to Nature or somewhere. Coronal heating problem solved. It's magnets, stupid. So that's. Is there anything else on the surface? Is that kind of our geography tour done?
Yeah, I mean, you can also get very bright regions, which are kind of the opposite of sunspots.
Is that where there's no magnetic field or little?
Well, I guess the magnetic field is lower there, yeah. They tend to kind of come complementary to sunspots,
Okay.
you know.
Oh, because bits gather up in one region,
Yeah,
so
and then
they're
they've left from another.
Got you.
Called plages.
Plages, like a beach.
Yes.
Is there okay? A plage.
Yep.
Right. Okay. I wasn't expecting that to be the answer. Why is it a beach?
I don't know. I can't remember my history.
So the sun has beaches now, is what we've learned from that. Jeez.
And they're all, referred to as types of stellar activity. All
Right.
these things that we're talking about. But that's pretty much most, points of interest on the surface, I'd say.
Okay. And then above that, we've got prominences and other things going on, flares.
Yeah, I mean, flares kind of occur over a range of regions, I would say.
Okay. It's not just something on the top, is that what you mean?
Well, because the electrons are channeled down the field lines to the surface of the star.
Right.
As we have defined it. And then the light flares upwards.
Nice.
So you can cover a range of regions there.
Yeah. Okay. Anything else? Any other space? I keep saying space. Any other stellar weather, solar weather?
The solar wind.
Indeed.
Yeah. So the solar wind is the constant outflow of material from the surface of the sun into space.
Nice. Well, that's just bits of the sun are flying off into space.
Yeah.
Are they still following field lines?
Yes.
Okay.
Yeah, they're still charged. So they're still following field lines. They follow what are often called open field lines.
Okay.
Which means, to all intents and purposes, they don't close. They don't go. They're open. If you were to draw a picture, they would just be a line that goes outwards.
That sounds like a magnetic monopole.
Yes.
Isn't one of Maxwell's equations, or the consequences of one of Maxwell's equations?
Magnetic monopoles are prohibited in physics.
Right. So that's two issues with physics we come up to today.
Yep.
So the sun is not real, is all we can say. Is that the magnetic field?
You're about to ask me a question.
Is that
that I was asked in my
your
viva of my master's project by one of the heroes and probably most intelligent people, it feels, in the department, and I couldn't answer it, and at the time it felt like I was just being an idiot, but with hindsight I wonder if it was meant to be a tricky question.
Okay.
I don't know. Of how can you have open field lines?
And the answer is?
I still don't feel like I can comfortably answer this question. But they're not really open.
They close somewhere.
They close somewhere.
So James Clerk Maxwell's still happy?
Yes, he's not turning in his grave. It's just that they essentially go to infinitely far away from the sun.
Right. So they're not actually...
I mean, it depends on your point of view, doesn't it? Are they actually or aren't they? If they go to infinity, they're never coming back. That's literally the point of infinity.
Yeah.
So this is why I feel uncomfortable with the question.
I guess if it ends somewhere, though, maybe it hops down on another star.
My Viva questioner was a theorist, so I think that was also part of it, that he knew that I, as a theorist, as someone from a theoretical physics background, rather than an astro background, which tends to be a bit more hand-wavy,
yeah,
would be very uncomfortable with this kind of question.
So they just wanted to make you sweat.
Yes, I think so, and it worked.
Okay. Still to this day,
Yeah.
flashbacks.
But these field lines essentially are open for all that we care. They potentially close at other points, like reconnecting with the other star's magnetic field, other stars nearby, or the Milky Way's intrinsic magnetic field. And then material flows out along them into space, and that's the wind.
So does the sun change much? Or does it sort of oscillate?
Yeah, so there's a thing called the solar cycle, which relates to the fact that the sun's magnetic field goes through a cycle every 22 years. So the magnetic field, you can think of it as having like a North Pole and a South Pole, like we do. And you could describe it as being like a dipole, which means that if you were to draw your magnetic field, it goes from the North Pole all the way around the sun, passes through the equator, and joins up to the South Pole. So you get like a lobe on one side, like an ear shape. And then you would have that on the other side as well, if you were drawing it on a bit of paper.
Yeah.
And that would be a dipole.
Because it's kind of like a donut, right?
Yeah.
Not a filled one.
In
a ring
in three
donut.
dimensions.
A torus.
Yes, it's a torus is what it actually is.
Which is not a ball.
That's a very simplified idea of what the field would look like. But at large distances from the surface of the star, the sun, that's a reasonable thing to draw. And basically, if you took that, over the course of its cycle, the North Pole and the South Pole will swap and then swap again. So that's kind of the same as taking your torus, your two earlobes, and then rotating them round like a clock.
Oh.
All the way round.
Right.
So that you end up with the poles, at the equator.
Yeah.
And then it rotates round again, so then the North Pole and the South Pole are swapped.
Yeah.
But the shape is the same as it was at the beginning.
Yeah.
It's just the two lobes again. But then it has to rotate again, around from like 6 o'clock around to 9 o'clock. So you've got the two lobes on their side again, and the poles in the equator. And then it rotates from like 9 o'clock to 12 o'clock.
So if you've got a ring donut and you've got sprinkles on top, you rotate it around, and then the next thing you know, it looks like a ring donut. But the sprinkles are on the bottom.
Down now.
And then you keep on going round, and now the sprinkles are back on top.
Yes.
Right. And that happens every 22 years?
Yes.
So that's from sprinkles up to
years.
sprinkles back up?
Yeah.
So 11 years, every 11 years it's like...
Every 11 years it looks the same.
But the polarity is the opposite way around.
Exactly, and that is the word for it as well. Good job.
Thank you. I've seen enough like sci-fi to be like...
The polarity is inverted.
Exactly.
Yeah. So you end up with these two cycles, basically. You have the magnetic cycle, which takes 22 years to get back exactly how it was. And you have the activity cycle, which takes 11 years.
Because the activity doesn't care about whether the dipole is aligned up or down, because what is up or down in space? It just cares about whether it's relative to the equator.
Yeah, it just cares about the shape of the field relative to... like you say, the equator, how the star is rotating.
Axis. Because I was going to ask, is it like the Earth, where the magnetic pole is kind of pretty much the same alignment as the rotational axis? Right. But...
no, it changes.
No. Really, no. I wasn't expecting that to be the answer.
It doesn't vary linearly.
Right, okay.
So it's not like...
it's not like a clock.
Yeah. It's not like every, inch it goes one way takes 1 minute or 1 year or something. The change is quite slow. Flip.
Right.
If you see what I mean.
It wants the magnetic pole to be more aligned with the rotational pole.
Yes.
It doesn't like it to be sort of aligned equatorially.
Yes.
So it's...
And we don't know how normal that is.
Right. Because
we
we've
don't
only got
know
the sun to
how
look
common that is. We do know about magnetic cycles in other stars.
at. Okay.
Not as much as you might wish,
Mm.
is the reality. We don't know that much about magnetic cycles in other solar-like stars either. There's no reason to believe that the cycles are going to look the same for a star like the sun compared to a really massive star.
Yeah.
Because those two stars are very different from each other in many ways.
But if something looks like the sun, you'd think it would behave like the sun in most ways. It could be a bit different. It could be like 57 years as opposed to 22 years. But it's not going to be like 1,000 years you would expect.
You might think, but we also don't know
Maybe it never
how
even
much
happens.
other things have to do with it, like the age of the star, because that changes quite a lot
Right,
of the
okay.
behaviour of the star. So we really don't know how normal that is. There's no reason to believe, looking at the sun, that it should be a particularly weird star.
Mm.
And so it would seem very logical that looking at other stars similar to the sun, you might expect similar kind of cycles.
Yeah. But we're also...
But you have to keep an open mind about the fact that we don't know that much about a
Yes.
lot of things. And so that might be true for some solar-like stars, but not all solar-like stars. And it might just not be true, that it might not be that common at all. You have to be open-minded.
You've got a piece of graph paper and you've put a dot on the graph paper and then you said draw a line.
Yes.
And you have no idea whether it's a straight line, a curved line, if there's even really a line.
Yep.
It-
And the sun, it's right there. We have a huge amount of data on the sun. I mean, there's always a joke in stellar physics that solar physicists have, so much data they don't know what to do with it, and that it actually, damages their, or delays their research progress, because for every theory that you could come up with or every explanation of something, there is evidence against that, because there is so much data. We collect so much information about it, and you can never, every explanation or model has to discount some of the physics. It can only include the most relevant physics,
You can't see the wood for the trees.
basically.
Yeah.
And I think part of it is that stellar physicists are really jealous because we don't have that much data.
Because you can come up with a theory and then it's only at the end of your academic career that somebody disproves that.
Yes.
Which point you retire with your pension, and
If that exists.
if it exists.
It's two extremes of, on one side, we have a lot of information about the sun. We don't know what to do with it. It's fantastic that we have so much data, but it does make life difficult sometimes. On the other hand, stellar physicists do not have enough data. we have data and we can make statements about things, we can make theories about things, but they end up being quite sweeping. Because there's kind of the opposite problem,
Yeah. Whereas observatories on Earth, you can get data every day on the sun
Yeah,
for
And they
maybe
do.
up to 12 hours a day, and then in space you can get it all day, every day.
yeah,
Whether that's a 28-day day or a 36-day day.
yeah. Yeah, I mean, also part of the issue with the sun, which is quite different and maybe not something that you've thought about, but it's going to be obvious once I say it.
Okay.
We have a lot of data on the sun, but we can't actually see all of the sun.
You mean we can't get around to the other side? Is there a dark side of the sun?
There are latitudes
Okay.
of the sun that we can't see. We can't see its poles. So there are latitudes that we have to kind of, the data is extrapolated,
Right.
Yes.
Because a lot of stuff is going... Yeah, because the stuff that's coming towards Earth is stuff that is light, which is heading directly in a direction. Whereas you might imagine that light coming from the surface of a sphere might be coming out normal to the plane, like straight out in a kind of like I don't even know what
Yeah.
you could say, but just like straight out from the surface. So, like at the pole, for instance, you might think that any light would go straight up and straight down, top and bottom, which the Earth is not directly above or below the sun.
Yes.
So, whereas the equator, we are presumably in the plane of the equator.
Pretty close, yeah.
So, not all, but like a lot of the light there is going to be most intensely coming at us, rather than, whereas other latitudes, it's mostly going out into space. We just got to deal with that.
Yeah, I mean, if you just think about how big, not necessarily massive, but how much bigger the volume of the sun is relative to us, and then our distance from it, if we're looking at the sun, there are just caps around the poles that we just cannot see.
Which is odd, because on Earth, and I don't know if it's to do with the light coming through the atmosphere or just that it's so intense when you look at the sun, which you don't do because it's bad, but it's a disc, it's a circle. It's not like, there's not like a sort of intense bit in the middle and then it gets dimmer. But I guess it's just so intense for human eyes, hence don't look at it.
Please don't look at the sun.
Okay, so we talked about different types of solar activity, and we talked about, at the end, the solar wind, but a slightly different wind that comes from the sun is, I guess, the photo wind, you might call it.
Yes, I suppose you could. Never thought of it as a wind before.
Yeah, well, when you were talking about the solar wind, that just made me think about solar sails.
Yeah, very cool.
Which don't use the solar wind. Apparently it does contribute a little bit, but it's very marginal.
Yeah.
So it's actually pushed along by photons.
Yes. Conservation of momentum.
Yeah, so as I imagine a lot of our listeners know, solar sails are concepts that have been used as well, where you have a large reflective surface in space attached to a spacecraft, and based on photons hitting the sail, it somehow magically manages to push the spacecraft in a direction, which, as you said, Ro, is based on the transfer of momentum.
Yes.
And I remember when I first heard of solar sails,
It blew your mind a little bit?
Yes, because
the idea that light, I'm guessing this is what blew your mind.
Yes.
The idea that light, which doesn't have a mass, could have momentum. Was that your...
Yes. So, if you just think about it in terms of everyday life, momentum is what means that when a car brakes, you keep on going.
Yes. And the reason why the car keeps on going more than a bike in a similar...
Yeah, and in terms of an equation, it's P, momentum, equals mv, mass times velocity. So it doesn't take much of a clever clogs to work out that if you have light, which is massless, you ain't got no P. But it turns out you do.
Yes.
So I had to go and look at this. But basically it's all a lie, everything you've been told.
That's how most science works.
Yeah. So,
although a lot of the time with physics it's not so much a lie, it's more that our understanding evolves, but we maintain to teach things in a certain way, in a kind of historical way.
Yes.
And so you learn things which are true in certain situations, and it's implied that it's true all of the time, but that's not actually the case.
Yeah. So that's exactly it. So in day-to-day life, you don't need to know this because that is what momentum is. P equals mv.
Yeah.
But actually, Einstein came along and he said relativity's a thing. And so because you're getting with light is actually at the speed of light. That's the
Yes.
that's
what it's famous
message from today's episode. But basically, P equals mv is an equation that works when an object is moving very slowly.
Yes. It's taking me right back to my special and general relativity classes here.
Fair.
Yeah.
So, yeah, and even E equals mc squared is a lie. It turns out that's also...
Yeah.
Is that when you're motionless as well?
Yeah.
So, yeah, and that's only for objects with a mass. It's all just crazy. Anyway, the point is that photons have momentum, and that's fine because it's basically the transfer of energy, as it were.
Yes. Yeah, so the idea is the light from the sun hits your sail, your reflective surface. It passes on energy that it had to the sail, and because there's a lot of light, that pushes your sail and therefore your spacecraft along.
Yeah. Yeah. So that was actually first, I think some people thought about it in like the 80s or something, but it was first used by JAXA's Icaros,
Yes.
which went to Venus in 2010. That was the first time that they put it onto a spaceship to actually do something.
I think that was a fact that I once knew
Mm.
and had reused the area of memory, so thank you for reminding me, because it's cool, isn't it?
It is. That was the first time that they actually used photons from the sun to actually try and move a spaceship. But actually it was important beforehand because missions, particularly sending missions towards the sun, like to Venus or Mercury, the momentum from photons actually will sort of blow your spaceship off course.
Right.
So even though they weren't using it to power the ship, they had to account for it.
That's very interesting.
To
Venus?
Yeah, so basically the closer
Wow.
you go towards the sun, the stronger the photons get because it's more concentrated.
Yeah, that's just geometric dilution, or the opposite, I suppose.
Yeah, geometric concentration.
Concentration, yeah. Yes. I just was surprised that it was important, even at the distance of Venus, but I guess that, makes sense if you can use it to travel there. It's late at night, brain.
Yeah, I think it's also that it's such a long distance as well. Like if you were just travelling a distance between, like, I don't know, London and Carlisle, then that's fine. You're not going to get blown off course. But, yeah, Venus. I think also even Mars trips maybe have to keep it in mind, but not as much as going inwards. The great thing about solar sails is that they're pretty cheap.
Yeah, well, you just get a big reflective thingy and
and
you're
that's
there,
it.
Really.
They can make your spaceship very fast, and they last a longer time than if you want to do any sort of movement or manoeuvres in space, then you need to have taken up some rocket fuel with you and have little rockets to propel you in different directions. So with the solar sail, so long as you've got a sail, then you're fine. As soon as you start to damage your solar sail, you've got an issue. But yeah, so they've actually thought about this being a good thing to get you out of the solar system.
Yes.
But the other thing that I find interesting is it is actually like sailing. You can actually tack into the solar wind, but not the solar wind, the photo wind.
As you've termed it.
Yeah, which I also don't understand how boats work. But It's, you go one way and then that way, so you go forwards.
Zigzag.
Zigzag.
And then you get where you're going.
You get where you're going. But one of the interesting ones as well is Light Sail 2, which is from the Planetary Society, which was set up by Carl Sagan.
Amongst others.
Yeah, Lou Friedman and Bruce Murray, apparently, in 1980. But most importantly, probably a bigger name than Carl Sagan, I would argue, it's now headed by Bill Nye.
The science guy.
The science guy. Which I remember at school, for some reason, they would wheel the TV in every now and again and be like, we could teach you about something, but why not put on Bill Nye the Science Guy?
So in classic, Rose is uncultured and knows nothing about what happens in, anything really that's cultural. I had not even heard of Bill Nye the Science Guy until I was at university.
Is that because you saw Big Bang Theory, or just met other people?
Yeah, it was Big Bang Theory, I think, and other people seemed to know who he was. I had just gathered that he was like some famous American science communicator, which is not far from the truth. I mean, that is, but I had no idea who he was until I was an undergrad.
Yeah, well, that's fair. And now you've explained to everybody that doesn't know that that's who he is. And I think also he
wears a bow tie and he's quite smiley.
If you have seen Big Bang Theory, I think he's in it as a cameo, maybe at least once. But there's also Professor Proton as a character. I think that's basically meant to be Bill Nye.
Or is it?
I think, or somebody similar. Science communicator.
Mm.
Anyway, Light Sail 2 is their sort of crowd-funded spacecraft, which launched in 2019, and it re-entered the atmosphere in 2022. But
on purpose?
Yes.
Okay.
Yeah.
You weren't clear there. So.
Sorry, yeah.
Right.
I think they kept it up for a bit longer than they had originally planned. But they had Light Sail 1, which went up into space, and they quickly found out some of the issues with how to make a solar sail, kind of thing. The central bit of the spaceship is the size of a loaf of bread. And
so not big.
Not big, but the size of the solar sail that is attached to it is the size of a boxing ring.
Right. I can see why this might logistically be a challenge.
Yeah, so it's actually so big that as well as actually managing to unfold it in space, which takes an amount of engineering apparently, because, you've sort of tried to origami it up, but it needs to... I think there's like a
Seeing
kind of...
things unfold in space is quite amazing, really.
Yeah. People have spent a lot of time thinking about it and also designing things to sort of make sure it goes well.
Yeah.
But the arms that keep up the solar sail, the booms, I think, they're so long that actually, depending on where it is and how much light is hitting it at a given point, the arms expand and contract in length.
Right.
So you also need to have a material that is able to
a bit stretchy.
Yeah. And it's less than the thickness of a human hair, which I think is something that people always say. But I think it's like 2 micrometers thick, so it's incredibly
People
thin.
say that a lot, and this is not really...
It's a thin thing that people know.
Not really important, but human hair varies in thickness quite a lot.
Okay, well, it's maybe thinner than the thinnest.
I never really noticed that so much until having a kid. But, the toddler's hair is pretty fine.
Small people, small hair.
Which I remember my sister's hair being. I don't know if it still is, but, pretty fine.
Yeah.
My hair is not. It's very thick.
Yeah. I've got incredibly thick chest hair.
What, the two hairs?
Yeah, both of them.
I don't know. Just grates on me a little bit that how unscientific that is, which, could be said with any comparison. But yeah.
Yeah. But the good thing about a solar sail is that because it lasts forever, obviously it doesn't, but it lasts for a long period of time, and you can use it to propel yourself as much as you want, kind of thing. That means that you can get into particular orbits. So the closer into the sun you get, the faster you need to go, not fall into the sun.
Yeah, you're in a higher energy orbit.
Yeah. So if you wanted to get to, say, the position of Venus and be in a stable orbit, then you would have to go at the speed of Venus. But if you want to stay in line with Earth, in a kind of geostationary orbit, as it were,
right,
but in line with the Earth, that is not the right speed.
What you're saying is the speed that your satellite has to, I'm saying satellite, but spacecraft, whatever you want to call it, has to go at, depends on which distance from the sun you want it to orbit at.
Yeah.
And if you want it to orbit close to the sun, then it has to have a higher speed to maintain the orbit.
Mm-hmm.
And if you want it to be further out from the sun, it needs to be orbiting at a slower speed in order to maintain the orbit.
Yes. But with the solar sail, what you can do is you can get close to the sun and still go round at the same speed as the Earth. But I think because you sort of angle your sail so that you're kind of being blown outwards, as it were, you overcome gravity a bit. So you no longer get pulled in to the sun going at a slower speed because you've basically got a rocket pushing you outwards all the time to overcome that.
Yeah.
But it is a rocket that never runs out of fuel because it's a solar sail. So what that means is you can then position a satellite closer in and be in sync with the Earth, which
I'm guessing is useful for things like sending messages.
Yes, so one of the main things is that what we didn't talk about in our solar activity part is actually that a lot of this solar activity can have effects for Earth. I think people generally know that if there was a massive CME or something and it hits the Earth, then all of our electrics go off, kind of thing.
The Carrington event.
Oh.
Famous one.
Is that an event that happened, or is that proposed?
Yes, it's the big famous one, the big solar storm that wiped out all of the US and probably other places, but the new, at the time, state-of-the-art fax system.
Nice.
Not fax system, telegram system.
When you say telegram, do you mean like the 1800s?
Yes.
Wow. So like there are people like in a Western saloon or something. They're like sending a message, and doesn't get through.
Crazy things happened. Yeah.
Yes.
Anyway, the reason I didn't talk much in it about the effect of solar activity on the Earth was because I felt that was in itself its own episode, really.
Yeah, I think so. And we can talk about why we don't get eradicated every day.
Yeah.
But basically, we would have like 6 hours warning or something.
Right.
Like that. If we had something there that could basically see that there was something coming directly towards us because it was coming towards it.
Mm-hmm. And could give us some measurements of things as well.
Yeah, and be like, watch out guys, you've got 6 hours to shut down all of your telegram systems, and then you can turn it back on again afterwards, kind of thing. So there's that, and also the other thing is that you could potentially use it for looking at any asteroids coming towards Earth, because whilst they are very difficult to see, I think you can see them just in IR because they're slightly above the temperature of empty space. I think you can see something that is coming towards the Earth because it's looking out towards the Earth. And
I see.
also, you've not got a lot of infrared noise or, massive intensity coming from the sun, I think, was what I took it to be. But,
Yes.
so
Sounds very useful.
That's one thing. The other thing is that you could potentially use it to very quickly get to the outer reaches of the solar system.
Yeah.
So currently it takes quite some time.
Many years.
But if you wanted to explore the moons of Saturn or Uranus or anywhere really, the idea is that you could slingshot around the sun, a bit like in Star Trek 4, The Voyage Home. But instead of going back in time, you go to the outer edges of the solar system really, really fast.
Yes.
Because it's not so much the gravitational effect, but it's that as soon as you go past the sun, you've then got a massive intensity of photons, which would just throw you straight to the edge.
Speeds up your spacecraft, and there's nothing to slow your spacecraft down.
Yeah.
So it just continues getting faster and faster.
The issue is, at the moment, we don't have the materials to make a durable enough sail. So that's not going to happen right now, but in the future.
Yeah. And one thing that space exploration has been particularly, amazing at is bringing us new materials. So, yeah. There's a lot of good potential there, a lot of hope that they could manage that.
Yeah. And the other thing that people have mentioned is that you could actually get, in a similar way, with lots of light, you could manage to get to another star.
Yes. This one is always brought up with solar sails.
Alpha Centauri isn't that far away in the grand scheme of things. And generally, when people propose this, they say, get a solar sail in space, you got it into space, and then you use giant lasers to irradiate the surface of your solar sail and just push it really, really fast. And I think the idea is that you could get pretty fast, pretty high level of speed. So there's one project called Breakthrough Starshot.
Yes, there is.
Which, the best bit about this, for me, is that they don't want to send one thing. They want to send 1,000 teeny tiny solar sail craft, all using lasers. And they think that if they could get up to 20% of the speed of light, I think it's like 15 to 20%, but if it was 20%, you could get to Alpha Centauri in 20 years.
Yeah.
And then you would just have to wait another 4 years for the light to get back to you. So you can find out what they found there. But also, we're sending
that's
things...
not that bad a wait, really.
No.
It's not the wait there.
I'll probably be alive in 24 years.
The crazy and...
The mega lasers.
Whatever part of that, yeah.
But,
it's a very ambitious project.
it is.
Let's put it that way.
Hey, NASA went to the moon not because it was easy, but because it was hard.
Mm-hmm. Just to clarify, Breakthrough Starshot is not a mission of NASA.
No, I think...
It's a private project.
I think... what's his name? Mark Zuckerberg. I think he has something to do with it.
I'm sure they all do.
It's all a bit weird. But yeah, also, I did hear Bill Nye, the science guy, say that if you did send something... at that speed towards another star, even if it's really tiny, the speed is so great that you're basically sending a nuclear warhead into another solar system. So if we're thinking there might be aliens there, because I think Alpha Centauri is one of the places that
sorry
has...
guys, there were aliens.
Oh, sorry. We're now at war with the aliens, but don't worry, they're 20 light years away or whatever. So 4 light
They're
years
4
rather.
light years away. They're not 20 light years away.
Sorry. So we've got a bit of time to prepare. Solar sails. The future.
Yeah. I mean, they genuinely could be. They're very... they're also the present, right?
Yeah.
They're remarkable things, and it's not only is it a cool piece of engineering and, a very simplistic and, in that sense, beautiful piece of engineering, but it's a lovely bit of physics as well. Again, with the simplicity of the idea and the science behind it.
Yeah. Apart from the fact that, as a teenager, Elliot's there thinking, this does not make sense. Light does not have momentum. It doesn't make sense. Turns out it does. So
But now you understand.
now I understand. The answer is it's relativity. So whatever you think you know, you don't. Because what you know is a very special case.
Take your Newtonian classical mechanics and throw it out the window.
Yeah. Instead, you need to think about what your twin's up to if they go on a rocket. So, I don't have a twin, so I don't need to worry about that one.
Well, thank you for sharing that with all of us. It was a fun...
Show and tell.
Yeah, it was fun. When you proposed, you were, the idea of talking about solar sails in one of the episodes to do with the sun. Yeah, I was quite excited because it is cool and something.
Yeah, and it's also not really that related to solar activity, apart from maybe the most important solar activity of there's a lot of light that comes out of it. So.
I think it connects nicely, though, and hopefully our listeners will have enjoyed it as much as I've enjoyed talking about it with you.
So that just about wraps things up for this episode. Please, can we encourage you to subscribe to Through the Telescope wherever you find your podcasts, and, if you like, you can leave us a nice positive review as well. It really helps the show, and it makes it easier for more people to find us.
Feel free to send us any comments, questions, or suggestions of things or people you'd like to hear about or from in future episodes. Or perhaps to put yourself forward to chat about your own astro research or experiences. As always, you can find us on Instagram at Through the Telescope Podcast, or you can find me at astrophysicist_Rose. You can also find us on Twitter at The Telescope Pod, and you can contact us by email at throughthetelescopepodcast@gmail.com.
And with that, we'd like to thank you very much for listening, and we look forward to seeing you again next time.
Bye.
Bye.